Okay, let's go through this problem 1.1 together. And I'll just be honest with you that there are probably different ways of doing this. I'll tell you how I thought about it as I, read the problem. So the first thing that I noticed is that I have a composite wall, and the wall has alternating layers of different materials. Obviously, these materials have different thermal conductivities. So we have fir, which is wood, aluminum, lead, and corkboard, and they have different thicknesses. And what we know is that on one side the temperature is 60 degrees C, and on the outside, that's 60 degrees C, and on the other side is 10 degrees C on the outside of the corkboard. So the question is, a couple questions are, what is the temperature gradient, and does the profile suggest any simplifying assumptions that might be made in subsequent analysis of the wall? Okay, so let me go ahead and do a sketch. So to me it looks a little bit like this. You have 4 different layers in this composite wall. The first one is 5 centimeters thick. I'll try to do this to scale. So the first one, my drawing is very wonky. Okay, so we have 5 centimeters of fir, which is a wood, and then that is next to aluminum, which is only 1 centimeter thick, which of course we know is a metal, and that's next to lead, also 1 centimeter thick, and then that is next to 6 centimeters of cork, also a natural material, a wood, like wood. Okay, and we know that at the one end it is 60 degrees C, so if we're using this as the temperature axis, and at the other end it's 10 degrees C. And the question is, what is the temperature profile, and simplifying assumptions in the analysis of the wall? Well, my first thought about that is obviously that aluminum and lead are going to be much more conductive than the fir and the cork. So, if I think about this, I know that any kind of heat that is transferred to the interface of the aluminum is going to be quickly transferred to the lead, quickly transferred to the cork. And so what I imagine is that actually most of the temperature drop will occur over the fir and the cork. Now, I kind of intuitively, I know that cork has a lower density than the fir, so I know that the cork has a higher air contact and probably a lower thermal conductivity. So I imagine that most of the thermal energy will be dropped over the cork. So in my mind, I would just say, okay, well, if I had to guess at the profile, it probably looks something like this, where at steady state, most of it will be dropped over the cork. Very little will be dropped over the lead and the aluminum. This is almost probably a flat line compared to the rest. And then over the aluminum, the fir, it would be dropped like this, so that the majority of the temperature drops over the cork. That's just a guess. So again, the simplifying assumptions for me is that the delta T total is going to be equal to the delta T of each of the slabs, and that for me, the delta T of the aluminum, the delta T of the lead, PB, plus delta T cork. Oh, this is very messy. Anyway, for me, my simplifying assumptions, but these two over the metals are negligible, so that I'm just looking at a temperature drop over the fir and the cork.